Stars are immense balls of hot gas, primarily hydrogen and helium. Deep within their cores, nuclear fusion occurs. This process powers stars and creates elements. Fusion happens when atomic nuclei combine to form a heavier nucleus. This releases energy, making stars shine brightly. The energy released is described by Einstein's equation, E=mc2. Intense pressure and heat bring hydrogen nuclei together. When they collide, they fuse to create helium, releasing energy. This fusion process creates elements. It's a continuous cycle of nuclei smashing together, transforming hydrogen into a dazzling array of elements. The most common type of fusion in stars is the fusion of hydrogen into helium. This process, known as the proton-proton chain reaction, is the dominant energy source for stars like our Sun. 4 hydrogen nuclei combine to form one helium nucleus, releasing positrons, neutrinos, and energy. The process begins with 2 protons colliding. One proton transforms into a neutron, releasing a positron and a neutrino. This creates a deuterium nucleus. Another proton collides with the deuterium nucleus, forming helium-3 and releasing a gamma ray. 2 helium-3 nuclei collide, producing helium-4 and releasing 2 protons. Each step releases energy, fueling the star's luminosity. This fusion is the first step in a star's life cycle. It's a process that has been ongoing for billions of years, creating the building blocks of everything we see. As a star ages and consumes its hydrogen fuel, it begins to fuse helium into heavier elements. This process, known as the triple alpha process, occurs at much higher temperatures and pressures than hydrogen fusion. In this reaction, 3 helium nuclei, or alpha particles, fuse to form a carbon nucleus, releasing energy in the process. The triple alpha process is a crucial step in stellar nucleosynthesis, as it bridges the gap between lighter elements like helium and heavier elements like carbon. Carbon, with its unique ability to form complex bonds, is essential for the chemistry of life as we know it. Once carbon is formed, it can participate in further fusion reactions, creating even heavier elements like oxygen, neon, and magnesium. These elements are then incorporated into the star's core, increasing its density and temperature. As the star continues to evolve, it becomes a cosmic cauldron, forging heavier and heavier elements in its core. This process of element creation continues, with heavier elements being synthesized from lighter ones, gradually climbing the periodic table. Each element has its own unique fusion pathway, requiring specific temperatures and pressures to overcome the electrostatic repulsion between the positively charged nuclei. As stars continue to fuse heavier elements, they eventually encounter a roadblock: iron. Iron is the most stable element in the universe, meaning it has the highest binding energy per nucleon, that's proton or neutron of all atomic nuclei. This stability makes iron the end of the line for stellar fusion. Fusion reactions release energy because the resulting nucleus is more tightly bound than the original nuclei. This energy release is what powers stars and allows them to overcome the immense gravitational pressure trying to collapse them. However, fusing elements heavier than iron requires more energy than it releases. Imagine trying to push a boulder uphill. With each push, you expend energy, but the boulder doesn't budge. Similarly, trying to fuse elements heavier than iron requires a tremendous amount of energy, but the resulting nucleus is less stable and wants to break apart. This energy barrier prevents stars from fusing elements heavier than iron under normal circumstances. It's like a cosmic stop sign, halting the steady climb up the periodic table. But the story of element creation doesn't end there. While stars cannot create elements heavier than iron through fusion, the universe has other ways of forging these cosmic heavyweights. Section 5. The Binding Energy Curve, Unveiling the Mystery. The inability of stars to fuse elements heavier than iron is best understood by examining the binding energy curve. This curve is a graphical representation of the binding energy per nucleon for all atomic nuclei. It shows how tightly nucleons are bound together in different elements. The curve reveals a peak at iron, indicating its exceptional stability. Elements lighter than iron release energy when fused, as the binding energy per nucleon increases. However, elements heavier than iron require energy to be fused, as the binding energy per nucleon decreases. Imagine a valley with iron at its lowest point. Rolling a boulder downhill, fusing lighter elements releases energy, while pushing it uphill, fusing heavier elements, requires energy. This analogy helps visualize why stars cannot produce elements heavier than iron through fusion. The binding energy curve is a fundamental concept in nuclear physics, explaining the energy release in nuclear reactions and the limitations of stellar fusion. It highlights the unique position of iron as the most stable element and a cosmic roadblock for element creation in stars. Section 6. Supernovae, cosmic alchemy at its finest. While stars cannot create elements heavier than iron through fusion during their normal life cycles, these stellar furnaces are not the only cosmic forges. When massive stars exhaust their nuclear fuel, they die spectacular deaths known as supernovae. These cataclysmic events are responsible for creating many of the elements heavier than iron. A supernova is a colossal explosion that occurs when a star's core collapses under its own gravity. This collapse generates immense temperatures and pressures, far exceeding those found in the cores of even the most massive stars. These extreme conditions provide the energy needed to overcome the iron fusion barrier and create heavier elements. During a supernova, a process called supernova nucleosynthesis takes place. This process involves a rapid capture of neutrons by atomic nuclei. Neutrons, being electrically neutral, are not repelled by the positively charged nuclei and can easily penetrate them. As neutrons are captured, the nuclei become unstable and undergo radioactive decay, transforming into heavier, more stable elements. This process continues, building up heavier and heavier elements including gold, platinum, and uranium. Section 7. Beyond iron, the creation of heavyweights. Supernova nucleosynthesis is a chaotic and rapid process with neutrons bombarding atomic nuclei at incredible speeds. This neutron capture process can occur in two main ways: the slow process or S process and the rapid process or R process. The S process occurs in the outer layers of dying stars, where the neutron flux is relatively low. This slow capture allows time for unstable nuclei to decay before capturing another neutron, resulting in the production of elements heavier than iron but lighter than bismuth. The R process, on the other hand, occurs in the extreme environment of a supernova explosion, where the neutron flux is incredibly high. This rapid capture overwhelms the decay process, allowing nuclei to capture multiple neutrons before decaying, leading to the formation of the heaviest elements, including thorium and uranium. These heavy elements forged in the heart of supernova explosions are then scattered throughout the interstellar medium, enriching the cosmos with the building blocks for new stars, planets, and even life. Section 8. The cosmic cycle of elements from stars to us. The creation of elements from the lightest to the heaviest is a continuous cycle driven by the life and death of stars. Stars are born from clouds of gas and dust enriched with elements from previous generations of stars. They fuse hydrogen and helium, creating heavier elements in their cores. When massive stars die as supernovae, they release these newly formed elements back into space, enriching the interstellar medium. These elements then become incorporated into new stars and planetary systems, continuing the cycle of cosmic evolution. This cosmic cycle of elements connects us to the vast history of the universe. The atoms in our bodies were once part of stars that lived and died billions of years ago. We are literally made of star stuff. Understanding the processes of stellar nucleosynthesis and supernova nucleosynthesis allows us to trace the origins of the elements that make up our world and ourselves. It's a testament to the interconnectedness of the cosmos and the remarkable chain of events that led to our existence. Section 9. Conclusion. The limits of stellar alchemy. Stars are incredible cosmic engines, fusing lighter elements into heavier ones, releasing the energy that powers galaxies and creates the building blocks of planets and life. However, even these stellar furnaces have their limits. The fusion of elements heavier than iron requires more energy than it releases, making it an energetically unfavorable process. This energy barrier, evident in the binding energy curve, prevents stars from forging these cosmic heavyweights through fusion. While stars cannot create elements heavier than iron through fusion, the universe has found a way to overcome this obstacle through the cataclysmic explosions of supernovae. These cosmic events provide the extreme conditions necessary for supernova nucleosynthesis, forging the heavier elements that enrich the cosmos. The creation of elements is a continuous cycle, driven by the life and death of stars. From the lightest element, hydrogen, to the heaviest, uranium, each element has its own unique origin story, forged in the heart of stars, or the fiery chaos of supernovae. Understanding these processes allows us to appreciate the intricate workings of the universe and our place within it.